Okay, so let's talk just a little bit about springs. So if you have a spring sitting on a table, you're not applying, you're not pulling on it at all, it's going to rest at its natural length. This is an equilibrium. And this is where it kind of like comfortably sits normally. So there are two things we could do to a spring. We could pull it out, we call this an extension, or we could squish it down, we call this a compression. And Hooke's law tells us the force that this spring is going to exert. So it says that the force of the spring is given by negative kx, where x is the displacement from this natural length of the spring. So we can think of the natural length as being where x equals 0. And then if we have an extension, so we're pulling it out further, the end of our spring is at some value x, which is bigger than 0. And Hooke's law says the force of the spring is going to be restorative, so going back towards equilibrium. The force of the spring is going to be given by negative kx. So this time, because x is greater than 0, negative kx is going to be to the left, back towards equilibrium. If instead we did a compression, we squish down our spring. In this case, the furthest point along our spring is at x less than 0. And so this is to the left of the equilibrium position shown here. And this restorative force is going to be now directed to the right. Okay, and so here x is less than 0. We're multiplying by this negative k value, or this negative number times k, which is going to be positive. And so we end up with something positive to the right. Okay. So k is called the spring constant. And it's going to be greater than 0. And so what this says is that the force of the spring is always linear in this displacement. Okay, so let's just take a look at how we set this up, and then we can think about the work done by this spring. Okay, so we're going to be assuming that we have some spring and it's going to be displaced 1 meter from its natural length. Okay, so this guy is 1 meter from its natural length, so x equals 0 is here. Okay, and in order to hold this spring in place here, we're going to be, we need to apply a 20 Newton force. And so what that means is that somebody is tugging on this spring 20 newtons to the right. Okay. What we would like to do is find the spring constant and an expression for the force that must be applied to achieve displacement of x, just in general. Okay, so just making a quick diagram of what's going on here. We are applying some force, 20 newtons. The spring is pulling back the other way, 20 newtons. I'm going to write that negative 20 newtons. Okay, because we're saying our spring is being held in place. So the amount that we're pulling to the right is being matched by our spring constant off to the left. Okay, and so let's put these pieces together. We're going to use Hooke's law to find our spring constant. So Hooke's law says F of the spring is equal to negative k times x. The force of our spring here is going to be negative 20 newtons. And if we take a look at what's going on here, we had negative k, and then our displacement was 1 meter. the right. All right, and so solving for K, we get negative 20 newtons over negative 1 meters equals K. And so just rewriting this a little bit, we get 20 newtons per meter is K. Okay, and now that we know our spring constant, we're actually able to write down, both the spring force, and then we know that the spring force, if we want to hold our spring out at some fixed displacement, we know that we have to exactly counter that spring force, and so we'll just change the direction. Okay, so let's write down an expression for our spring force. Okay. It's going to be negative 20 x. Okay, so it's negative the spring constant times this displacement x. Oops, and notice that it's a little bit confusing here when we just write just f. We're going to write this f of x because it depends on our displacement. Okay, and so we're able to write down our spring force for a displacement of x. And so if we want to actually, if we want to hold on to this displacement of x, our counter force is going to just be the equal size, but the opposite direction. So the force that we're going to apply to hold it at this displacement is going to be equal to 20 times x. Okay. All right, great. Next, let's look at how we compute the work done.